Good evening, everybody. All right, it's 7 o'clock, 6 o'clock in Denver. So we're going to go ahead and get started here in a couple minutes. I just want to just double check technical, so forth. Can everybody hear me, see me, so forth? I apologize for the really, really boring wall behind me. We've just moved into the new house and I haven't really set everything up in my office yet. So do me a favor, send a quick message into the chat box here on the right. Let me know if you're here, if you can see me, if you're having any problems, and we'll get started we'll go ahead and wait 2-3 minutes, okay? Tell you what, I'm gonna go put the dog away and I'll be right back in about 5 minutes, all right? Make a quick note. All right, Michael, cool, thanks. Let's see, let's adjust this just a little bit. All right. All right, so Michael can see me. I'm going to just assume that everybody else can. All right, like I said, we're going to wait about another minute or two and just see if anybody's going to show up a little bit late. Get this all started. All right, so we are ready to go. I do have to say I am very sorry that I had to cancel the webinar for last week at this time. The move has been more challenging than we had thought it was going to be. So we just got Wi-Fi service a couple days ago. I still don't have a washer and dryer in the house, but I do have a refrigerator, so that works. But as you can see behind me, so forth, we have boxes everywhere. I'm still living out of a suitcase, been here 2 weeks. So, but I'm happy to be here tonight, and we're going to go ahead and get started in just another minute. A couple more people have joined in, so welcome. And yeah, like I said, we're going to go ahead and start here in just a couple minutes. We are going to talk about hydroponics tonight and nutrient calculations. So I hope the information is valuable to you. Quick check. Has anyone not received the automatic download of the nutrient manual, the cheat sheet manual you were supposed to get it in an email download after you registered for the webinar and confirmed on the list. So if you haven't gotten it, make sure you send me a message and I will email that out to you as soon as this is over. All right. Well, I'll tell you what, it is 6:05, so why don't we just go ahead and get started. Okay, so this is a free webinar. This is me trying to help you guys understand how to calculate and mix your own nutrient solutions, because frankly, when you buy nutrients in a hydroponic store, most of the time you're getting a big bottle of water that has a little bit of nutrient in it. It's valuable and it's worthwhile, but in the end, you're paying a very inflated price because the manufacturer has to ship water across the country. And then it sits on the shelf in the hydroponic store and it takes up retail space and they have to charge for it. So if you can mix your own nutrients, you can save 80–90% of the cost of buying the nutrients in the store. It's a massive savings. Plus, you get the benefit of being able to customize the nutrient solution for your specific water chemistry, for your specific crop or crop varietal, and you have control that you wouldn't otherwise have. by doing this and matching these calculations up with consistent water testing and evaluation of your crops, you can end up getting better production, better growth than you ever thought would be possible. So we're going to be here about 90 minutes, maybe a little bit less. We'll see how fast we can go through it tonight. I'm not going to rush, but if we can go through it faster, then we will. You will get a replay from this webinar. So about 30 minutes or so after we sign off and get done, you will get an email out that will have a link to the replay. It's not going to be up forever. It's going to be up for 7 days, 7 days only. So from now until, or from tonight until 1 week from tonight. So if you want to review, I just want to be clear, want to warn you, I'll say it again at the end of the webinar. The replay will only be available for 7 days. So if you want to watch it, make sure you watch it. Other than that, let me tell you a little bit about myself so you kind of understand where I'm from, where I'm coming from, and why I should be giving you this information, why I have any value. So I've done aquaponics for a little over 8 years now, closing in on 9. I've taught agriculture, math, science for over 15 years now. And the last 2 years I spent as the lead faculty at Santa Fe Community College, leading the controlled environment agriculture program, where we taught commercial scale hydroponics and aquaponics for production, for food. It was all for food. We didn't work on anything related to anything else you can grow with hydroponics. We focused just on food, but the techniques do work for all hydroponics. The math involved with mixing and calculating your own nutrient solutions, when I started looking at this 2 years ago, I was amazed at how simple it was. It's one formula that you use 2 different ways, but it's that one thing, those 2 ways, over and over and over and over again. So it's not a super complex or challenging process. It's a series of steps that, once you understand the basic process, you can use to do anything. And when I recognized that, and then we started looking at the cost, mixing our own nutrient solution for a 350-gallon system where we grew lettuce and basil and so forth in our classroom. We were able to mix up a 3-week nutrient batch for, I think we calculated it, and I don't remember exactly what it was, but it was like $2.10 for a 3-week batch of nutrients for 350 gallons. It was nothing. And now, granted, yeah, you have to buy the 50-pound sacks of nutrients and so forth to begin with, so you're going to have a capital cost. But by and large, if you have a production farm, if you've got 5, 8, 10,000 gallons of water in a production facility doing NFT lettuce or tomatoes, cucumbers, anything like that, you're going to go through a 50-pound sack of nutrients in a few months. I mean, even still, if you've got under 500 gallons of nutrient solution for $1,000 capital outlay, you're going to have nutrients for probably a year and a half, 2 years, and that's it. And you'll have a lot more left over than that. And I mean, okay, the $1,000 is probably a wrong number to say. It is really, really inexpensive, and we'll show you that towards the end of the webinar. But that's me. Like I said, I've been doing this for 8 years, and I've been in education for over 15. So I like teaching. I like being able to pass the information around, and that's really what I want to do. So we're going to go ahead and and bump over to the slide deck. So I'll be able to see the chat box. So if I'm going too fast for you, if I didn't explain something well, you want me to go back a slide and go back through things, just use the chat box. Let me know that you're there. Actually, right now, I see that there's 17 people here with us right now, but Michael is the only one who's let me know that he can see and hear me. So just a quick check. Can everybody else see me? Can you see me? Give me a quick thumbs up or a heck yeah, something in the chat box to let me know that you're here and you're getting me. Hopefully. Yay, Matthew can see me. Anybody else? Is it just the two of you out there? All right, we're going to go ahead and slide this over to the slide deck. Let's see. Let's bring this up. All right. So you should be able to see the slide deck. Yeah? Let's see. While we're doing that, I'll tell you what, I don't know about you guys, but to me, it's looking like that might be a little small. I don't know. You think that's okay? Yeah, we'll see. We'll leave it like that. Let's see if I can make this any bigger. That makes it seem bigger. All right, we'll leave it like that. Okay. So over the last 8 years that I've been doing this, I have written a lot of course materials for aquaponics, and for the last 2 years, I wrote all the curriculum for the Santa Fe Community College program. And due to the budget issues and so forth in New Mexico, that is what precipitated me leaving New Mexico and coming back to Texas. But I have decided that I want to be able to provide all of this out. So I'm going to be working to transition a lot of this out to an online format. So I'm going to be doing a lot more webinars like this. So if there's other topics or things that you guys want to see, let me know. Drop me a note, drop me an email. But what this is basically one tiny little part of the 3-course sequence that I taught in hydroponics. Between my intro class, the chemistry and plant deficiencies class, and the advanced production class, it was basically 3 semesters worth of hydroponics. So this is one lesson out of one little part of that. And it's one that I think is very valuable. So today we're going to talk about formulating nutrient solutions. Now, in that, it's important to understand what essential minerals and essential nutrients really are. It's a term that I've heard thrown around quite a bit back and forth. To be an essential nutrient for a plant, you have to do these 3 things. The plant can't complete its life cycle without it. The action of the element must be specific, meaning that you can't replace it with something else. And that element must be directly involved in the processes of the plant. So it can't just make something else more available or more useful. It has to actually be used and directly involved with the plant. That's what makes it essential. Now, there are only 16 elements that are considered essential, really. Now, there's a little bit of argument and debate. Some people say that there's a 17th essential element. They add nickel into the micro element list there on the right. The resources that I've read and used and so forth, they say 16. So unless somebody puts a new element in the macro column, honestly, it's really not that big of a deal. And we'll get to why that is in a moment. But of these 16 elements, it's pretty much an arbitrary line that divides them into macro and micro. But macro, you need lots and lots and lots of it. Micro, you need very, very little. The macro elements, they're in that column there on the left: carbon, hydrogen, oxygen, nitrogen, phosphorus, potassium, calcium, sulfur, and magnesium. Okay, carbon, hydrogen, and oxygen, they're on the list. They are macro elements required by plants, but you can basically ignore those. The carbon and oxygen come in through CO2, so that comes in through the atmosphere. The hydrogen and the oxygen comes in through water, so you don't have to worry about that. You have to provide the bottom 6 on that list, from nitrogen down to magnesium. Now, the micro elements are there on the right. These are the ones that you need them. If you don't have them, your plants are going to be just sickly and just bad. But you really don't need much. Very, very, very small amounts. So you'll see exactly what I mean by that when we get to the calculations. All right, now these next couple of slides, I put them in here so you could have them as a resource to review with the replay and such, but I am not going to go through and read every little bit of what each element does in the plant. I'm just going to kind of hit the high points. Nitrogen is part of basically everything. Anything that's made of protein has nitrogen in it, but it's also found in DNA. It's also found in RNA. It's also found in chlorophyll. Nitrogen's found in basically everything. Phosphorus is used in, once again, just about everything, but it's also used in the phospholipids that make up the cell membrane around the individual cells. So it's super important. Potassium, that and calcium are actually also used to provide power. They're used to convert solar energy ultimately into chemical energy, whether it's directly solar energy or breaking down sugars and such. But sulfur, magnesium works in the chlorophyll molecule the same way that iron works in hemoglobin in our blood cells. It's the central atom that really makes chlorophyll work. Calcium is used in the cell walls. It's also used to help with the energy creation. Iron is used for a lot of different things. It's required in the process to make chlorophyll. And chlorine, manganese, they do a lot of different things. Boron. I have read 7 different papers on how boron is used in plants, and those 2 sentences are the best I can give you as to what boron is actually used for in the cell. Nobody really knows. What I do know for sure is that if you don't have enough boron and you try to grow something that is going to that has flowers, that you're trying to get to fruit, if you don't have boron, your flowers are going to fall off the plant and you will have no fruit. For whatever reason, boron is necessary for pollination and for flower set or fruit set with flowers. Zinc, copper, molybdenum, they're micros. You need tiny little amounts of these. And then carbon, hydrogen, and oxygen, I put those at the end because they're in everything. Literally, they are in everything. But since we don't actually have to provide them in our solutions, we don't really have to worry about it. Okay. So the whole reason we're here is to figure out how to make a valid, valuable nutrient solution for your plants. The reason we are trying to get the right amount of nutrients for your plants, the reason we're trying to calculate out and get that perfect Goldilocks amount not too much, not too little, is because we don't want our plants to be deficient. We don't want them to be malnourished. We've all seen the pictures on TV and so forth of dogs and horses and people and such that have been starved, that are deficient in different minerals or food or so forth. They're not growing. They're not healthy. Well, it's the same thing with our plants. If they don't get what they need, then they're not healthy, and they're not going to grow as fast. They're not going to grow as big, and they're certainly not going to produce as much fruit. So the nutritional disorder is it's a malfunction in the physiology because you have not enough or too much, deficiency or excess of an essential element. Diagnosing these is a little bit more challenging. And that could be probably a 2 to 3 hour presentation in of itself of how to diagnose. There are a lot of resources out there that give you a key on how to identify, okay, my plant's doing this. What deficiency is it? One of the quickest and easiest things that you can do when you're looking at your plants is looking to see whether or not it's a mobile or an immobile element, because some of the deficiencies will look the same, they just show up in different places on the plant. So a mobile element means that the plant can scavenge that from its existing tissues. Means that it can take that element specifically from the older leaves and take it out of those tissues and move it up into the newer leaves. So if you are deficient in nitrogen, magnesium, phosphorus, potassium, zinc, any of those, your older leaves, the bigger leaves, the ones in the bottom of the plant, those are the ones that will show that deficiency first. Using nitrogen as the example. Nitrogen, if you're deficient in nitrogen, the leaves of your plant turn yellow. They get this pale, sickly green, and then they just go yellow, like banana yellow. But it's the older leaves. The young leaves, the brand new growth, is going to be perfectly green and it looks healthy. But what happens if it's the other way around? What if the old leaves are green and it's the young leaves that are yellow? Well, in that case, you have an example of an immobile element. What that means is that at one point the plant had enough of that element, i.e. the older leaves, the older tissue, and it was fine. But now it doesn't have enough. So now the new growth is deficient. It can't move it. So once it's locked into the tissue, it's there. It's not going to move. So if your young growth is yellow, you are deficient in iron. So a lot of people mistake an iron deficiency for a nitrogen deficiency. And they add extra nitrogen into their system and their plants don't look any greener. So to solve that, you add iron. Now, that being said, just to say, in 8 years of running my own aquaponic systems, I have never, ever supplemented one of my aquaponic systems with anything other than a little bit of iron. And when I say a little bit, I'm talking like a tablespoon of iron every 2 to 3 weeks for a system that's, 1,000 gallons. Not much. When I was at the college and we were doing production in our system, so forth, we put in more iron, but that was more just a preventative. We were just making sure we were also growing some things that were very, very heavy feeders on iron. So there was that. But in general, if you're doing hydroponics and you're mixing your nutrients correctly, you really shouldn't have nutritional disorders. You really shouldn't have any deficiencies at all. A couple little things. I have seen several commercial tomato farms, hydroponic tomato farms that grow a couple rows of cucumbers on the same in the same greenhouse on the same system as their tomatoes. And the reason for that is that cucumbers are very, very sensitive to both boron and calcium deficiencies. Uh, One of the farms in northern New Mexico said that their cucumbers would actually show deficiency symptoms almost a full week earlier than the tomato plants would. So they grew the cucumbers for profit. I mean, they sold them, but their primary purpose in the greenhouse was as an indicator to make sure that the system was running appropriately so that their primary profit crop, the tomatoes, never faltered, never had an issue. So when they saw if they ever saw an issue with their cucumber plants, they knew they had more than a few days, to adjust their nutrient solution so that their tomatoes would never have a problem. And then that bottom one is also important. What happens when you get tired and stressed out? Do you get sick easier? Do you have worse reactions to a virus or to whatever? Well, of course you do. If you have plants that have been recently affected by pests, by aphids or caterpillars or so forth, and they're stressed out or weakened in some way, they will be more susceptible to nutrient deficiencies than others. And it works the other way too. If you have plants that are showing nutrient deficiencies for whatever reason, they are going to be more easily infested by pest insects than strong growing plants, than vigorous plants. So the weaker the plant, the more, the easier it will be to have an issue. All right. So now we're going to get into the chemistry. All right. It's 6:30. So we've got about another hour. This is the part where if you have pen and paper, if you have a calculator, it would be good to get it out. I've done all the calculations out and so forth, but even still, if you do them along with me, it will help you understand the calculation and the process that much better. Now, I know that a number of you have probably not seen a periodic table in more than a few years. So that's why I put this up here. Periodic table, in terms of what we need for hydroponics, those two rows at the bottom, the lanthanide and actinide series, you can ignore those. We're never going to worry about those. And then you see that pretty blue turquoise color that runs kind of diagonal down the right side. Okay, pretty much that line, and then up and to the right, the blue, the light purple, and then the other two purples going towards pink. Those are all the non-metals. That means those are, well, we'll just leave it at that. Those are the non-metals. So the green, the yellow, the orange, and then that left column of pinks, those are all the metals. Now, when we talk about salts with hydroponics, a salt is just a really general chemical term for a metal element that is bonded to a non-metal or a series of non-metals. That's all a salt is. It's a metal and a non-metal together, basically. What you can get from the periodic table. Let me move to the next slide. On any of those boxes, so any of the boxes that you see on here, you can see that there's the number at the top, and then the abbreviation, and then some things below it. So this is what you're going to get. That number at the top is the atomic number. Now that tells you where it is in the periodic table, the number of protons that are there. For us, we don't need to worry about it. We can ignore that. C, in this case, is the symbol. That is the abbreviation for the element. It's not always the first letter of the name of the element, which is the next thing on that box. For example, potassium. The element potassium has a symbol of K. The element P, or the symbol P, stands for phosphorus. So you have to be a little careful. It's mostly intuitive, but there's a few that are odd. And then really the most important thing on this box for us is the atomic weight that's down there at the bottom. That tells you, well, just that, the weight of one atom. So it uses a unit called an atomic mass unit, an AMU, which, well, not to put too fine a point on it, is a really, really small amount. Really small. So the number is important. The unit for the weight, really not that big of a deal. All right. So I've gone through all this. I forgot I had this all broken down. So let's go forward. So the atomic number is the number of protons. That's also the number of electrons that are in there. And the atomic weight is the atomic weight minus the atomic number gives you the number of neutrons. Those are the different pieces of the atom itself. It'll help you do some things, but we don't really need it for the calculations. So, all right, let's go through this. Now, it is not really useful to put elements into your nutrient solutions because elements are generally, you're not going to find them. They're a single kind of atom. It's 100% carbon, so a diamond or graphite. There is nothing else there. It can't be broken down into other things. Like I said, we're going to be using salts, which a salt is a compound. It's a substance where two or more elements have been bonded together. So water, carbon dioxide, sodium chloride, magnesium sulfate. All right, all of these things are compounds. They have two or more elements that have been bonded together. And then a mixture is actually what our nutrient solution is. We take water, H2O, and we're going to add 4 or 5 or 8 or 12 different salts into that. So we're going to make a mixture. It is multiple substances, 2 or more substances that are mixed together but not bonded chemically. So in our case, it's a solution. It's that mixture that provides everything to the plants. All right. So where did I draw all this information from? I'll be honest with you. I am not the creator of any of this. This book is a great one. Hydroponic Food Production by Howard Rash. Howard Rash has done so much for hydroponics in not just the US, worldwide. This was my textbook when I taught at the college. This is a great, great book. You can buy it on Amazon if you would like. Tell you what, if anybody wants to buy it, so forth, shameless self-promotion. I'll send out a link. I am an affiliate seller on Amazon, but in your replay email, so forth, I'll send out a link to buy this. It doesn't add anything to the price. It just says that I sent you to it. So if you want to buy it, go for it. If not, I don't mind. But chapter 3 is all about nutrient solutions, and it's all about calculations. So his method and his explanation is not dramatically different from mine, which makes sense because I used his book as the resource to write this whole lecture. But mine is a little bit simpler and more straightforward. but that's one chapter out of 12 in his book, and the other 11 are excellent. So what we're going to work on from here to the end of the webinar is I'm going to show you the formula and the steps necessary to actually calculate a nutrient solution from scratch. While doing this, we're going to go through the math that is necessary to make the adjustments, to make the solution, so forth. And hopefully you will get the understanding of how and why we do that, why we do things the way we do, and the process. There is a little bit of art to this. The steps are easy, but knowing which salt to use, when to switch to something else, or go back or go forward, so forth, there's lots of different ways to go through the same recipe, and there's not really a right or wrong. There are ways that are easier, more challenging, but everything works. So find your own way. If you think that there's something that I'm doing that's more confusing or more challenging than what makes sense to you, do it your way. Go for it. But if you're confused, try it my way. Try it the way I put forward on the slides that are coming up, and I really believe that you'll end up getting it. So let's start with the difference between a fertilizer and a hydroponic nutrient solution. So if you're a soil farmer and you're going to go out and fertilize your field, you're going to go buy a fertilizer that has an NPK ratio: nitrogen, phosphorus, potassium. So for example, NPK 13044 means you have 13% nitrogen, 0% phosphorus, and 44% potassium. Now, in common fertilizers, that nitrogen comes out as NO3. Phosphorus is the P2O5 because it's a very stable molecule. And then the potassium is the potassium oxide, once again, because of the stability. Now, in hydroponics, we'll use nitrogen as nitrate, but every now and then we'll also use it in ammonium, the NH4. Phosphorus comes from a different source. We can get phosphorus by itself, or we can get phosphate, that PO3. And then potassium, well, since it's dissolved in water, we just have potassium, which works because all of those in the hydroponic side are more easily absorbed by plant roots than the P2O5 and the K2O. So that's part of the reason that we do it this way in hydroponics. It's also partially because that's just the way things dissolve in water. All right. So this right here, that's the equation. That's all it is. It's a proportion. You have A over B equals C over D. And that's really all it is. We have the amount on the left side, and we're converting it into an equivalent amount on the right side. Now, I'm going to skip forward for a second so that we have a frame of reference to use that formula. This is the formula that we are going to calculate in this webinar. This is a real basic, simple lettuce solution that Resh uses in his book. We used this at the college, and we grew both vegetative plants, lettuce, basil, bok choy, Napa cabbage, sunflowers, sorrel, a bunch of different stuff. But we also grew peppers. I grew tomatoes and so forth, but I just grew the seedlings, transplants. I never actually flowered them and did fruiting with this recipe. But this is a great basic recipe. So if you're just doing vegetative, this works. But take a look at those two columns. That's the macros on the left and the micros on the right. So remember earlier when I said the difference between the macro and micro is that kind of arbitrary line of you have a lot of the macros and very little of the micros? Well, it should be pretty obvious at this point where that line is. You know, we're talking 200 parts per million calcium. We're talking 0.05 of 1 ppm of molybdenum. So a lot of calcium, a tiny, tiny little bit of molybdenum. Now, we're going to start our work with calcium. We want to get 200 ppm calcium in our nutrient solution. Now, to do that, we have to get our salts. And I apologize. That's just irritating me to have that out of the way. All right, now that I've got that fixed. We have to get our salts somewhere. So not going into the big chemistry terms, so forth, of how to name all of these, so forth. If you just search the names, you'll find them, okay? But we're going to go with calcium nitrate, which has the formula Ca and then NO3 parentheses 2. Now that I do want to go over. Okay, so these subscripts in that salt formulation. So if you see a number in a chemical formula, if it is a number that is below a subscript, below and to the right of a letter, then it denotes how much of the element right before it you have. So take a look at that second one down, the KNO3. All right, we have a 3 subscript, but it's behind the O. So that means we have 3 oxygen. So potassium nitrate has 1 potassium, 1 nitrogen, and 3 oxygen. But now look up at calcium. So the 3 means we have 3 oxygen, same as in the KNO3. But we have that parentheses, and we have a subscript of 2 behind the parentheses. So that means we have 2 of whatever is inside the parentheses. So calcium nitrate has 1 calcium, but it has 2 nitrogens and 6 oxygens. So that's just something that you have to be aware of. And then this is something that you need to write a note for yourself, put it down, put a sticky note somewhere on the side of your desk. 1 ppm, 1 part per million, equals 1 milligram per liter. And they're equivalent. They mean the same thing. But we're going to use both sets of units in our calculations, and here's the reason why. ppm is generally used to denote concentration, how much of something is in a volume of water, right? 1 part per million, 1 part per thousand, so forth. Milligrams per liter is going to tell you how much you need to add per volume of water. So we're going to use that unit when we talk about how much of a particular salt do we need to add in order to get a certain concentration. All right, so what do I mean by that? Well, here we go. Starting off, we need to know what the weight of calcium nitrate is. So we use our periodic table. The weight of calcium is 40.1. The weight of nitrogen is 14.0. The weight of oxygen is, well, it's technically 15.999999. So we just round everything to 1 decimal place, so it becomes 16. So the weight of the salt, calcium nitrate, you have 1 calcium, you have 2 nitrogens, you have 6 oxygens. So that's a total of 164.1 grams per mole. And you know, I actually I'm just going to take that off because I told you we're not going to worry about units here. Okay, so we just take that off. Now, our formula calls for 200 ppm calcium. So that's what we need to get in our solution, 200 ppm calcium. The slide just before, we calculated that the molecular weight is 164.1. And right, if we go back to that slide, if we're going to look at how much calcium nitrate do we need to get 200 ppm of calcium, well, we probably need to know the weight of the calcium itself. So we've got three things. 200 ppm of calcium is what we're looking for. The weight of the calcium nitrate salt is 164.1, and the weight of calcium itself is 40.1. So now we just need to know how much calcium nitrate we need to add. And that's where our formula comes in. So here's our ratio. Here is the basic formula. The ion you're looking for over the salt that it comes from. And that equals the concentration goal, right? The ppm goal for that ion. And then X. And X represents the amount of this salt that you need in 1 liter of water. Now, basic math, basic algebra, if you divide anything by itself, it cancels out and becomes 1. So the grams per mole for the ion, the grams per mole, excuse me, for the salt, they cancel out. We basically have no units on the left. I did explain why we keep the units on the right, even though they also technically cancel out. But let's put some numbers in. Okay. So the first thing you need to do, and especially if you have any confusion in you whatsoever, write this down. Write down all the steps that I'm showing you. If you do the same steps every time in the same way, it's like muscle memory. You don't have to think about it. You just kind of flow through it time and time again and time again, and you don't get lost. And if you do ever make a mistake, and I'll be the first one to say I still make mistakes, but if you make a mistake and you've shown all of your work, it makes going back and finding where you made your mistake so much easier. All right, so that being said, sorry, that's the math teacher in me. Too many years teaching math. So we start off by writing the specific formula that we're doing. Calcium over calcium nitrate, ion over salt, equals our ppm goal over X. Step 2, you plug in your numbers. The weight of the calcium ion, 40.1. The weight of the calcium nitrate salt, 164.1. The ppm goal of calcium, 200 ppm. And then we have our unknown. We have the one value that we don't know. Now, to solve this, like I said, it's been a while since a lot of you took chemistry. It's probably been a while since most of you took an algebra class. So if you remember how to cross multiply, cool. That's the process that you're going to use. You're going to cross multiply, you're going to solve for X, and you'll come up with 818.5. Now, for the rest of you that have no idea what I'm talking about when I say cross multiply, I made the next slide. Cross multiply is exactly what it sounds. And you know, since I'm going through and correcting things, I'm going to flip that around because that's really what it should be. Yeah, come on. Turn. There it goes. You're going to take the bottom number and multiply it with the top on the other side of the equal sign. So 164.1 is multiplied by 200. X is multiplied by 40.1. That gets rid of the fraction. So now we have everything on the same level of the equation. Now to get X, so that brings us from that step 1 with the red and yellow arrows to step 2. Now that we have step 2, we need to solve for X, meaning we have to get X by itself on one side of the equal sign. So we divide both sides by 40.1. Remember, anything divided by itself is 1. So 40.1 divided by 40.1, it cancels out. It disappears. We're left with x. But on the right side of the equation, you have 164.1 times 200, but then this is all divided by 40.1. And if you do that on your own, if you do that with your calculator right now, 164.1 times 200 divided by 40.1 gives you 818.5. Now, this is milligrams per liter of calcium nitrate. You know what? I'll go back and fix that later. But 818.5 milligrams per liter of calcium nitrate. So we need to add that much calcium nitrate for every liter of solution that we're trying to mix up. And that'll be a later part. But now what do we do? Calcium nitrate doesn't just give us calcium. So calcium nitrate does give us calcium, but it also gives us nitrogen in the form of nitrate. So now this is the second format. So like I said, it's one formula. Ion over salt equals ppm over x. But we're going to use it two ways. The first way we use this equation is like this, right? Where we know the ion we're looking for, we know the salt we're using, and we know the concentration we're supposed to have. So we're looking for how much salt gives us this concentration. The second way we use this formula is like this, where we know the ion, nitrogen, we know the salt, calcium nitrate, we know how much of the salt we needed, right, in the previous step to get the right concentration of the first element. But now we're trying to say, with this much of the salt, what concentration do we get of the second ion, nitrogen in this case? So this is where that subscript becomes really important. Nitrogen, we actually have two of them in every molecule of calcium nitrate because it's Ca parentheses NO3 taken twice. So 2 nitrogens over calcium nitrate. So 2 times 14 and over 164.1. We use the 818.5 milligrams per liter because that's how much calcium nitrate we need to give us the calcium that we need. Well, now we cross multiply and solve for the ppm. So the 818.5 is multiplied by the 28 up here, the 164.1 down here is multiplied by the ppm up here. Then we solve for that value and we get 139.7. So what does this actually mean? Well, I've got a summary on the next slide. So that bottom piece that I had on the previous slide, right, that told us that we have a ppm value of 139.7 of nitrogen. So our recipe wanted 165 ppm of nitrogen. So we don't have enough, but that's okay. So we have to make a note here. We still need some nitrogen. Well, the 165 minus the 139.7 is 25.3. Now, 25.3, yeah, I rounded it up to 26. it's not going to throw you off. If you do 25.3, if you do 25, if you do 26, let me just go down a rabbit trail for a second. Okay. Most of you are probably going to be using a basic little gram scale that you get at Walmart or Target or off eBay or Amazon, whatever, but it's going to measure 2 grams. If you get a really, really good one, you might measure to 1/10 of a gram. I seriously doubt that any of y'all are going to get a digital scale or so forth that'll measure to a 1/100th of a gram. If you have the gram scale that I have, the little kitchen scale that I have, it measures to 1 gram. You know, I couldn't measure out 818.5 grams if I wanted to. So the level of error, the margin of error is not something that you need to worry about that drastically, in my opinion. So if you want to use 25.3, go for it. If you want to use 26, 25, go for it. You want to be close. You don't want to just throw stuff together, but at the same point, if you want to round everything to whole numbers, you're going to be fine. Okay? You're going to be fine. So in the end, we still need a little bit of nitrogen left. We still need to find a little bit more nitrogen for our solution. So now we need to pick a second salt. So we go back to our formula. Now our second salt is going to be potassium nitrate. Now there's actually hundreds of salts that you can use. And like I said before, there's really no right or wrong way to do it. It's just what you want to do. It's what you want to do. It's what you are able to get, so forth. So I like using calcium nitrate first because it's easily available, it's cheap, and it's a pretty high quality product that you can get for inexpensive. Potassium nitrate is my next go-to because, once again, it's easily available and it's cheap. All right, so we're going to set this up the same way we did for potassium, or for calcium nitrate. It's ion over salt equals concentration in ppm over the x, over the unknown mass, the amount. So the weight of nitrogen is 14.0. The weight of potassium nitrate is 101.1. The concentration that we're looking for is, it's that 26. Sorry. So you could put 25 or 25.3 here if you wanted. And then our unknown. We cross multiply again, 101.1 times the 26, x times 14, and we end up with a 187.8 milligrams per liter of KNO3. So that was the nitrogen in KNO3. But now we need to go the other direction. If we have this much KNO3, in order to get that concentration of nitrogen, well, what concentration of potassium do we have now? So we go here. Now we have a new element, potassium. We look at our periodic table. The weight of potassium is 39.1. And we plug the values in. Potassium over the salt, ion over salt, 39.1 over 101.1. Now we're trying to figure out what concentration of potassium we get out of the given amount of the given X value of KNO3. And we solve and we get 72.6. So now let's go to our summary. Well, 72.6 is the ppm that we're getting for potassium, but we need 210 ppm potassium. Well, we're going to need more, obviously. Well, the 210 what do we have here? There's our summary. The recipe wants 210. We just got 72.6. So we need to find 137.4. And we go from there. Now, here's where the artistry comes in. Okay, so let me go back a few slides to the recipe itself. Actually, yeah, let me go forward. So, well, yeah, I'll just go with this since I'm here. Calcium, we got some potassium. Magnesium is one of those where I recommend you do the magnesium pretty early in your calculations, because you have, in the commonly available salts, you have one salt that gives you calcium, that's calcium nitrate. You have one salt that gives you magnesium, and that's magnesium sulfate, also known as Epsom salts. But you have 3 salts that give you potassium. You have a potassium nitrate, you have a potassium phosphate, and you have a potassium sulfate. So here's the reason why, after we did KNO3, the potassium nitrate, why I jumped to magnesium. And the reason for that is, if I went ahead and got the remainder of my potassium using potassium phosphate and potassium sulfate, well, then I would have way too much sulfur when I go and get my magnesium. So, little thing about nutrients and nutrient solutions. I have yet to find a recipe of somebody else's that, when I mixed it up with the salts that I was able to get, the purity levels that I was able to get, so forth, and adjusted for what was already in my source water, I have yet to find a recipe that I can make work perfectly. They're always a little bit off. I'm over with a little bit of this or under with a little bit of that, so forth. And in the end, my plants always grew fine. There were a few times where I went, okay, I've got a little too much sulfur in my water, or I don't have enough calcium, or I don't have enough potassium. And I would make a note and I would adjust it the next time I made the nutrient solution. So to kind of go down that path for a second, once again, this is really the strength of mixing your own nutrient solutions, being able to mix your own nutrient solutions. You have the ability and the power to adjust from one crop to the next how your plants grow. You can look at how they're growing. If you have a deficiency show up, or you have an issue show up, or whatever, you can add more or less of a particular element the next time you mix the solution. If you're just going to go buy, green grow juice from Fox Farm at your local hydroponic store, well, you can only add that. That's all there is. But if you're mixing your own, you have more control. And in the end, that's really what we're all wanting with hydroponics. That's why we do it, is so we can have the control. If we go back to this with magnesium, and I'll just run through this because it's the same process. Ion, okay, if we look at that first proportion on the slide, ion over salt equals ppm concentration goal over X. Plug in your numbers, the weight of magnesium, the weight of magnesium sulfate equals the ppm goal, the 40 ppm from our recipe, over the unknown. Cross multiply and solve. So 405.8 milligrams per liter of Epsom salt. Now, that much Epsom salt gave us the 40 ppm of magnesium, but it also gives us 52.8 ppm of sulfur. All right, if we go through this whole process, I'll slow down a second so you guys can write this down, because I know I'm going kind of fast on it, but it's the same process over and over and over again. Part one, you use the ppm goal from your recipe to figure out how much of that salt you need. Part two, once you know how much of the salt you need for that first element, you figure out what ppm you get of the second element in that salt from the amount you calculated in part one. And then you adjust your recipe as needed. If you didn't get all of a particular element, and then you move to the next one at part one, and you just go through that part one to part two to part one to part two, over and over and over again. All right, so when we do our summary, we still need a little over 60 ppm sulfur, so we just mark that down. And so now we look at this, and so calcium, magnesium, and nitrogen are green because we've gotten those perfectly. Potassium and sulfur are in red because we've gotten some, but we don't have all. So I've adjusted this to show how much more we need to get of those two elements. So we still need 133.4 ppm potassium, the 50 ppm phosphorus, and the 60 ppm, 60.2 ppm of sulfur. So now we do monopotassium phosphate. You could have done the sulfur one, but I like to get phosphorus first. And mainly because I want to make sure that I can get the phosphorus. So I know I'm going to get potassium with this, but I want to make sure that I get the amount of phosphorus that I need. So we go through all of this, ion over salt, ppm over x, and we end up with 219.5 milligrams per liter of the monopotassium phosphate. So that's part one. Now part two, if we have that much monopotassium phosphate, what ppm of potassium are we going to get? So we run the part two. Well, K over KH2PO4, ppm over X. We solve for ppm, and we get 63.1. So now we go to our summary. Let me highlight this down here at the bottom. So our recipe said we needed 210. Now remember we got the 72.6 from the KNO3. We just got 63.1 from the monopotassium phosphate. So 210 minus 72.6 minus another 63.1 means we need 74.3 more ppm potassium, right? Okay. So now we go to our last one, potassium sulfate. Now potassium sulfate is a K2SO4. So we get 2 potassiums for every 1 sulfur. So we multiply the 39.1 weight of potassium by 2. So ion over salt equals ppm over x. We needed the 74.3 more potassium, so that was our ppm goal. And that means that we need 165.6 milligrams per liter of K2SO4. Now, we put that in for sulfur. So this only gives us 30.5 ppm of sulfur. Well, here's the problem. We needed 113 total. We got 52.8 from the magnesium sulfur, or magnesium sulfate. And we just got the 30.5 ppm from the K2SO4. But we are nearly 30 ppm short of sulfur. So we don't have enough. This is actually not a big deal. I have run solutions that were short of sulfur, by 40 or 50 ppm, and I didn't really see any issues with my plants. When I was in New Mexico, hey Ryan, I just saw your comment. You watching this several times is going to be worthwhile. It's not a super challenging thing, but it does take some time going through it. But I love that. I love your comment. Uh, just saying, when I was in Santa Fe, the tap water, the city municipal water in Santa Fe had 60 ppm of sulfur in it naturally. So it already had all the sulfur I could pretty much want for most recipes. So I can't stress this enough. And this isn't really a part of this presentation and so forth, but when you do your calculations and you do your solutions, get a water test. You need to know what's in your water to start with. Once you know what's there, you adjust your recipe for what's already in your water, and then you add in the rest of the nutrients. That way you're not wasting anything. I mean, I know aquaponic farms that are, they're not around anymore, but one in particular that was at the bottom of an agricultural valley, and the water it pulled up out of its well, going into its fish tanks, had nitrate at like 70, 80 ppm. And they basically didn't even need fish to grow their plants because it was already there in the water. So check your water. And yeah. All right. So here's where we are right now. Calcium, magnesium, potassium, nitrogen, phosphorus, we're good. We got everything. Sulfur, we're nearly 30 ppm short. Okay, we need to make a note of that. Not a big deal. Now, I'm not going to go through the individual steps on the micros, but it's the same process. Actually, it's even easier because the micros are such small amounts that even though you're going to use a copper sulfate, putting in 0.1 ppm copper, the amount of sulfur that you're going to put into solution is nothing. You might be short 29.7. Well, if you put in your 0.1 ppm copper, you might be short 29.65 ppm sulfur. It's with the micros. Just worry about the element that's there: the iron, the manganese, the copper, the zinc, the boron, the molybdenum. Don't worry about the other element in the salt, because frankly, the levels are so small, it's not even an issue. So how do we turn this into something that will allow us to mix a recipe? Well, we have to take our X values and turn that into a mass that we can actually use. So here's our summary chart so far. The calcium nitrate, potassium nitrate, monopotassium phosphate, potassium sulfate, and Epsom salt, magnesium sulfate. And this is the milligram per liter that we calculated for each one of these. Now, you'd probably go through and do this over here, and you'd even have H3BO3, boric acid, and you'd have copper as well. But okay. Oh. Take that back. That was where we were going to end. Well, I'll tell you what. We went through, well, you know what? I'm going to modify this slide, but while I'm doing that, to add in the next part, let me know if you have any questions. Give me a shout. Did I go through anything too fast? Did I, where are we? What do you think? All right. So I'm gonna change this into an example where we've got a 300 gallon system. All right. Let's see, Ryan. Okay, Ryan, that's actually what we're going to do right now is how to convert milligrams per liter into the mass of salt that you need. Michael, you posted a question. Oh, oops, that was on the other screen. I didn't see that real quick. So okay, okay, Michael, you asked how do we know what the ppm that we need per nutrient? And then Ryan, that goes actually along even with your question about what are you aiming for, so forth. Okay, so what you're going to want to do with these is you're going to go find recipes. There are recipes out there in published journals. There are probably 40 or 50 recipes for various crops, so forth, that are in Resh's book, in another book called Hydroponics, a practical guide. And you're just going to find them. They're out there. And they're out there for all crops, food as well as ornamentals and other crops. But once you find a recipe, then you can modify it along those lines. So we're running a little low on time, and this is going to take a couple minutes. So let's go through this, and then I'll do a couple other things. All right. So let's start with this. If we're talking about a 300-gallon system, well, gallons doesn't convert to liters very easily. Well, it does. I mean, there's a simple calculation, but the basic idea is that 1 gallon equals, so you know what, hold on. I'm going to put that down here so it doesn't mess things up. So conversion. Sorry, hit the wrong button. So if we're converting 1 gallon, that equals 3.785 liters. So that means that 300 gallons is 1,135.5 liters. Now, the formula we're going to use to convert milligrams per liter into an X, which is grams. Let me delete that. So well, if this is where we want to end up, what we need is a conversion formula, a conversion box. So let's see how to do that quickly and easily. Basically, what you're going to do is you're going to make a box, and think of it as a series of fractions. All right, we'll just do it like this. We've got milligrams over liters, and all right, bear with me because I'm trying to make fractions and make this work. So, all right. So basically we've got milligrams per liter so far, right? Why is my computer freezing? We need to convert units. We need to get from milligrams per liter up to grams. But we need to also multiply this by the 300 gallons. Now, we know that 300 gallons is 1,135.5 liters. And so that's how many liters we have. So that's really over, it's a fraction, over 1. Everybody with me so far? So if we have 818.5 milligrams per liter, then this is really what we're doing. Now, anytime you divide by the same thing, it cancels out. So liters and liters cancel out. So when we do this, this liter cancels with this liter. And they disappear, and we can ignore them. So now we just need to convert milligrams into grams. Well, so we're going to multiply this again. And let's see. So converting milligrams to grams, grams to milligrams. With metric, the prefix milli is 1,000. So there are 1,000 milligrams in 1 gram. We need milligrams to cancel. So that's the beauty of this method of unit conversions. Where does 1,000 milligrams go? Where does 1 gram go? Well, if we have milligrams on the top here, the 1,000 milligrams has to go on the bottom over here, because it has to cancel. So now let's do this in a different color so we can see that that cancels. Let's do blue. Yeah, it shows up. So now milligrams has canceled, and we're left with grams, which is what we want. So when we do this out, right, we now have, if we just look at the numbers, we have 818.5 times 1135.5 times 1 over 1,000. And that's just because I don't have a divisor, a division sign easily. So I put this down here so we can see what we're doing. And I will move this over here, get it out of the way. All right. All right, so there we go. So all of that equals, do my calculations real quick, 818.5 times the volume divided by 1,000 gives us 929.4 grams of calcium nitrate. So in order for us to mix up 300 gallons of solution using this recipe, we need 929.4 grams of calcium nitrate in order to get 200 ppm of calcium in that solution. Okay, does that make sense? That to turn this X value here into the amount of salt that you have to add, you have to convert milligrams to grams, and you have to get rid of the liters, which means you have to figure out how many liters are in the solution that you're mixing up. Ryan, you were going to swell my head, man. That's awesome. And it's really that simple. There's a lot more details to this. Just to tell you, there's purity, there's this and that and so forth. But all right, so we've been here almost 90 minutes, like 85 minutes at this point. So I want to just say, this is something that I really want to do. This is something that I've enjoyed doing for the last 8-10 years of my life, teaching. 15 years actually is how long I've been teaching. It's not anything specific that I've come up with, but I think I'm more than decent at presenting it in a way that makes it easily understandable. So what I'm going to be doing over the next, I don't know. Here, tell you what, I'm going to shut down this because I want to talk to you guys for a second. So where is, there it is. All right. Nope. There it is. Okay, so what I'm going to be doing over the next 6 months, 8 months, I'm going to be converting all of my classes from the college, all of the aquaponic workshops that I've done, and to be honest, anything else that you guys request and want. I'm going to be converting all of that into an online format where you can log on, your schedule, your time frame, so forth, and get it all. This is what I taught as a 2-year associate's degree at the community college, and I'm going to put it online. So you can get it. It's not accredited. It's not a university degree or anything like that. It's just the information, which is what most people want. Most people don't care about the degree specifically. They just want the info. So that's what I'm going to give you. So I want to offer you guys a special deal. Yay, I know. Every webinar has a sales pitch at the end, and I'm sorry. But I want your feedback. Ryan, I love seeing comments like the one that you said, so forth. I like helping people. That's why I'm doing this. That's why I'm a teacher. So if you switch down at the bottom of the screen, there's a little tab that says offers. I want to let you guys have a chance to actually buy this entire module. Now, this is what we just did was one lesson out of the entire thing, which actually, let me bring this back up a sec. I want to show you this. So this is actually what the module, or what you would actually get. Okay, that's really small, so I'm going to make this bigger. I want to give you the opportunity to buy this module, this 4-lesson module, for $10. I've got it listed for 20 right now. I'm going to give you guys a special coupon code. The coupon code is nutrients, lowercase, nutrient with an S at the end, nutrients. If you want, follow the link down there at the bottom, the one where it says buy here. Click that and go check out, so forth, enter the coupon code, and it'll bring the price to $9.95. It's an email-based class, so you will get, once you sign up every 2 days, you'll get a lesson. It will be a video lesson that will have the slide deck and so forth, and it doesn't go away. Once you get access to it, you have it. You get the videos. But lesson one, as you can see, is essential elements, beneficial elements, periodic table, and calculating molecular weights. We did a little bit of that today. We didn't talk about beneficial elements. So that's something that's really changing the way a lot of people look at hydroponics these days. Lesson two is using recipes to make the solutions. So where to find the recipes, the value and importance of water quality testing. And then the calculation portion is the majority of what we actually did today. And then the final thing on that is how to adjust for the purity of the ingredient. So that's a little wrinkle that we didn't talk about today. Lesson three is finishing that up. It's volumetrics. So the little bit that we just did at the end where I put that together on how to make a solution, well, there's that. But we also talk about making concentrated solutions so that you can make a 100x concentrate or a 1000x concentrate, and you only have to mix nutrients once every 2 months, 6 months, so forth. Saves you a lot of time. And then we talk about solubility. So, okay, well, if I can make a 1000x, well, could I make a 10,000x concentrated solution? Well, that you run into some chemical issues there. And we talk about that. And then lesson four is adjustments. So you notice this about your plants and you want to back it off like this. Or my well water just changed and now I've got, 75 ppm sulfur and 45 ppm calcium and so forth. So modifications. And then the second half of lesson four is identifying nutrient issues. How to identify an acute deficiency versus a chronic deficiency. How to identify toxicities, having too much of an element. And then you'll get a bonus email and this is actually not part of the module. This is part of the bonus for you guys. You sat through 90 minutes of me blathering on. You get a recipe book, 5 of my recipes. Lettuce, cucumber, tomato, a couple others that I've thrown in there. And you get my recipes, both worked out and the recipe, the ppm values itself. So that's it. All right, let me pull this back up. So that's it. That's my sales pitch. $10. And here's why it's $10. I've done free classes. I've done free workshops. I've given information away left and right all over the place. And in the end, when I do something for free, invariably, nobody cares. Nobody goes home and practices. Nobody does it and so forth. Ryan, click the button that says buy here. You see the button that says buy here, right? Oh, wait. Did I not put the Did I not put the link in? Oh, hold on. See, this is the other thing. I'm not super great with technology. So here, we'll do this. Let's go back. And there you go. So don't worry about that's also because I didn't even turn it on. Yeah, so I needed to do that. There you go. So now the offer should be there. I never turned it on, but I just put the comment there in the chat box. In any case, why am I charging for this? Anytime I have charged for anything, whether it was a $10 tour of my farm to a $500 weekend class, if in my experience, what I've seen is when people pay for it, they value it. They do the work. They pay attention. And I wanted to make sure that you guys valued what I'm giving you. So that's what it is. If you want to sign up and get it, the class starts see, today's Thursday, so the class starts on Monday. So lesson 1 will get emailed out on Monday. And other than that, you guys have my email now. The webinar Ninja emails come straight to me. So if you ever have an issue, so forth, email me there. I'm here to answer questions. And like I said, I want to be able to provide the information that you want, that you need. So if you have a question, if you have something that you want to know more about or so forth, let me know. Shoot me an email. Cool. All right, guys. I want to thank you all very much for being here, spending 90 minutes with me tonight. And I will be here next time you have a question. I'm probably going to get my house in order and set up my shop and a couple of demo systems. So keep an eye on the Facebook page. If you haven't followed it already, Green Phoenix Farms on Facebook. Follow my website. You guys are already all signed up for my email list, and way to go. But I'm going to be building a microgreen production rack in my garage. I have some products that I'm going to start testing, lights and other such. I'll tell you more about that in the future. And then in my backyard, I'm going to be building a whole series of DIY projects. So over the next 18 months, Green Phoenix Farms is going to roll out a whole bunch of projects that are going to be DIY videos. How to make a Dutch bucket system using 5-gallon buckets. How to scavenge in your local community to find buckets from bakeries or donut shops or so forth. You know, where to go find materials. How to build stuff on your own in a functional but inexpensive method. Now, my wife is going to make sure that the aesthetics are there somewhat, but function is going to be the bigger priority. So we're going to have a lot of fun. But keep an eye on the Facebook page. Join our new Facebook group, DIY Ponics. The DIY Naturally Aquaponics is a great group. They're good people. But DIY Ponics is my group, and that's where I'm going to be putting out a lot of special offers next time I do a free webinar, things like that. And yeah, so all right, guys. Thanks. Have fun. And send me an email if you have any questions. Talk to you soon. Have a good night. Bye.